could the whole universe be thought of as a chaotic system? If it can, does it also have a chaotic, a strange, what's called a strange attractor, a fractal attractor in cosmological state space? This, the trouser state space, but for very large, large trousers, if you like. And are the laws of physics? So this is the key point. Could the laws of physics, at their most fundamental, be describing the geometry of this fractal, cosmological fractal? And could that provide us new insights? So that's what we can talk about into quantum mechanics. I do believe it can. If that's right, it's saying that this geometry is the fundamental quantity, and that's a property of the whole universe. It's everything that's in the universe all together.
Welcome to Closer to Truth. I'm speaking with Tim Palmer about his visionary, expansive, and yes, brave new book, The Primacy of Doubt, From Quantum Physics to Climate Change, How the Science of Uncertainty Can Help Us Understand Our Chaotic World. Tim challenges conventional wisdom in quantum mechanics and free will. I love it, which does not mean necessarily that I believe it. Welcome, Tim. I look forward to discussing the book. It really is terrific.
Thanks, Robert. It's good to be here.
Let me start with just a brief bio for everyone. Tim is a Royal Society research professor in the Department of Physics at the University of Oxford. Trained as a mathematical physicist, he pioneered the development of operational ensemble weather and climate forecasting, which are now standard best practices globally. He contributed to the Intergovernmental Panel on Climate Change's Nobel Peace Prize in 2007. Tim, we have lots to cover, and I want to go through this book in detail, but let's start by unpacking the title and its comprehensive subtitle, bigger than most books, but there's a lot there. So let me repeat it for everyone. The Primacy of Doubt, which is the title, and the subtitle, From Quantum Physics to Climate Change, that's quite a jump, how the science of uncertainty can help us understand our chaotic world. So let's start with this. You have doubt in the title and uncertainty in the subtitle. Please distinguish between these two concepts.
Well, I don't distinguish particularly between them. The title actually was, I've lifted the title from one of my all-time favorite quotes, which was from James Glick's biography of Richard Feynman. And in it, he said that he, Feynman, believed in the primacy of doubt, not as a blemish on our ability to know, but as the essence of knowing. And that's kind of been a kind of theme of mine over my career. I've had a sort of somewhat varied career covering a lot of different topics, from fundamental physics to applied physics. And uncertainty has been a kind of constant theme through all of that. So I've tried to write a book which, where uncertainty is the dominant theme. But, that James Glick quote about Feynman, his belief in the primacy of doubt, was such a marvelous quote. I couldn't help but lift those words for the title.
Well, doubt has sort of a psychological implication and connotation, where uncertainty, the way you're using it, becomes very scientific. That's the distinguishing concept that I see, that doubt is this overall vision of presenting everything. And that's, I think, the very last sentence in your book, you come back to the word doubt, which was wonderful. It was a very nice rounding out. But uncertainty then is the dominant scientific theme as you develop. Okay, next, you say the world is chaotic, and I think anyone who is sentient on the planet would feel that is an uncontroversial statement. But you mean something much more scientifically about the word chaos and chaotic. Just give us a very brief overview.
Well, this actually goes back into the 20th century, where it was realized that many systems that look completely as if there was no order or no kind of form governing their behavior, because they just fluctuated completely irregularly. My old colleague Bob May, who was a world-renowned ecologist, applied this to populations of biological systems that seemingly boomed and bust with complete irregularity and unpredictability, but showed that there's order. There is actually an order underlying that, and there are kind of equations which describe that and describe the disorder. The weather is another example. You look at a time series of weather, it looks like it has no sort of structure to it. The weather changes erratically from one day to the next, 1 month to the next. But we know perfectly well there are underlying equations. So it's that sort of tension between what looks as if there's no order and the fact that underlying that there is order. And that's
Yes,
kind of
and this is a fundamental principle of the book, and indeed a deep insight into the nature of reality, because the word chaos in common usage, the connotations, means no order, but in fact the whole theory of chaos theory is to develop the internal order and to understand what that means, and that's really the foundation of the book, and that's wonderful. Okay, so the next phrase you have in the subtitle is the science of uncertainty, which is somewhat related, obviously, to chaos theory, but define that exact term, the science of uncertainty. How is that developed? What is the mathematics? Very briefly.
Well, I think what is quite a common perception about systems, could be like the economy or the global health, or indeed weather, and other ones, is that they seem to evolve in a reasonably ordered and predictable way for long periods of time, but suddenly become extremely unstable and unpredictable. So we get financial crashes, we get devastating weather events, we get world wars. Perhaps we're on the brink of something now. I don't know. The question is, how can science deal with that particular aspect? You see, if uncertainty was just the same every day, if we could just put a standard error bar on any prediction we made and it was the same error bar, I mean, there wouldn't be that much interesting science behind it. The interesting part about the science is that the uncertainty can be virtually zero for long periods of time and then explode to extraordinarily large values intermittently. So when I talk about the science of uncertainty, it's kind of, I suppose, if anything, focusing on that particular issue. Why is uncertainty so variable, and why can it suddenly explode where for long periods of time it's kind of relatively benign?
Yeah, and that's the theme in the book, and we see that over and over again. You develop it in the first part, kind of theoretically, and then apply it. It's a wonderful approach. All right, I'm still on the title. We have a long subtitle, so I haven't finished yet. So the last part of the subtitle is the science of uncertainty, which you've just described, and now you're applying it to quantum physics and climate change, which sounds like an odd combination, because let me give you my conventional wisdom thinking on this. Now, in quantum physics, conventional wisdom is that there is fundamental randomness, unpredictability in principle at the most fundamental levels, yet exquisitely predictable when summed over all the possibilities at macroscopic levels, and we have all sorts of proof of that in everything, in our cell phones, everything else we're doing today. Whereas in climate change, the unpredictability is chaos theory, which is certainly fearsomely complex to predict as a practical matter, and ever more complex, but its unpredictability has a different connotation to it, and it doesn't seem to be fundamental. So the uncertainties in quantum physics, again, conventional wisdom, are fundamentally different from the uncertainties in climate change. Now, that's the conventional wisdom, and I think you challenge that. Is that right?
That's right. I challenge that, and I have worked. My PhD was in the borderline between quantum mechanics and gravitation theory, so I have a kind of background in that. And you're right. The standard conventional wisdom is that climate change, weather prediction, the uncertainties are what philosophers call epistemological. In other words, it's the fact that we don't know everything about the system that creates the uncertainty. Whereas the orthodox thinking in quantum mechanics is that it's the actual equations are uncertain, and the phrase then would be called ontological uncertainty. Of course, Einstein hated that. That's why the whole phrase "God does not play dice" is just saying this notion of ontological uncertainty is just crazy. I mean, who asked for that? It's just a bizarre idea when you think about it. So I do challenge the reasons for orthodox physics thinking that quantum uncertainty is ontological and therefore different to chaotic uncertainty.
Okay, so this I want to put that in everyone's mind because we're going to get into that a lot deeper later because that's a fundamental point here. I'm just trying to give an overview so we can understand where we're going. So now what I want to do is do a brief architecture of the book. We spent the first period of time on the title. We spent a lot of time on the title and subtitle. Now we're going to get into the overarching architecture of the book. You have three parts. So just give me a sense of what you are trying to accomplish in each of these parts. Begin with part one, the science of uncertainty, where you talk about three specific important ideas.
That's right. I want to, the first part is kind of introducing the science of chaos. So some of this, as I say, was, people may have, for example, James Glick, who I mentioned, wrote the biography of Feynman. He also wrote back in the, I think, 1980s, a really wonderful book on chaos theory. So I cover a little bit of that, but I try to cover some other things. And one of the really, I think, fantastic discoveries in 20th century science was the fact that there's a kind of geometry underlying these chaotic systems. So we talked about order. There's order in chaos, and the usual way when scientists talk about that, they talk about the equations that govern the evolution of chaotic systems. But in my book, I want to actually, what I do is talk about something which I view to be even more fundamental than a set of what are called differential equations, and that is the geometry. There's a certain geometry to chaos. And it's a geometry in a kind of slightly abstract space called state space. And this geometry is an example of a fractal geometry, which means that you kind of zoom into it and you see structures reappearing. And that kind of geometry underlies pretty much everything else in the book. So I try to really describe, the Ed Lorenz, who was the meteorologist at MIT that discovered this geometry, how he went about discovering it, and what a fantastic, I kind of rank it up there with Einstein's relativity and Schrödinger and Heisenberg's quantum mechanics in terms of just the extraordinary discovery of it. And then in the other part of the book, so the other aspect is I try to distinguish between what's called low order chaos and high order chaos. So some systems are very simple. They have very few equations, but they still can be chaotic and unpredictable. A good example is a pendulum. If you have a pendulum, but instead of having a single sort of strut going down to the pendulum, you put a joint halfway up the pendulum. So there are actually two separate kind of bits that can swing backwards and forwards in a slightly independent way. That actually is an example of a chaotic system. The bob oscillates extremely irregularly, but it's a very simple system. On the other hand, if you have something like the weather or the economy or whatever, that is a very complex system. And what I try to show is that if you want to represent those systems in an approximate but realistic way, it's actually good to introduce noise. So noise is another theme of my book. The notion that noise actually can be a positive, constructive resource in many situations and not the nuisance it is. And for example, in weather and climate models these days, we actually introduce noise deliberately into the models to make them more realistic. And later in the book, I talk about the role of noise in the brain as a potential resource that the brain uses, and maybe it's the critical thing that makes us the creative people we are. So the first part of the book is about that. I try to do it without any mathematics, but it's a kind of involves, if you like, mathematical concepts or fractals and things like that, and the role of noise in complex, like turbulent fluids and things.
Good. Right at this point, I think it's helpful to explain very briefly ensemble forecasting. I put that in your bio. That was perhaps one of your great contributions to the society of the world, not just theoretical mathematics and physics and chaos theory. Just describe that very briefly, because the achievement there, I think, exemplifies many of the principles you're now speaking about.
That's right. Well, I worked for many years in an international operational weather forecast center. And when I joined, the kind of paradigm at the time was that you use all your computer resources to make the best possible single weather forecast that you can. You make the model as complicated as you can, given the computer resource, and every day or every 12 hours, actually, you make a single weather forecast, and that's basically, and you might make it for a week ahead, something like that. And what used to bother me was what I just mentioned earlier, that you can get systems which are predictable for day after day, and then suddenly become extremely unpredictable. And I said, well, we're at prey to one of these events. We put out a forecast which actually will turn out to be completely and utterly wrong, because we've entered an exceptionally chaotic part of the climate, attractor, the thing that governs the evolution of weather. And sure enough, actually, there was in the UK, there was a remarkable storm, one of the worst in 300 years, which was completely unforecast, even 12 hours before it happened. It was extraordinary. And that, I think, suddenly made people realize we've got to do a better job at this. We've got to actually put error bars on our forecast, and we've got to be able to do it in such a way that we can see these extremely unpredictable events in advance.
Tim, so ensemble forecasting is the perfect segue into part two, which is predicting our chaotic world, in which you apply that concept of ensemble forecasting to a whole series of different things. Again, just the overview of part two.
That's right. I mean, the idea of ensemble forecasting is to try to predict ahead of time whether we're in a predictable situation or potentially heading into an extremely unpredictable situation. And it was something that, didn't happen for many decades in weather forecasting development. And to some extent, it's helped by the fact that computers were getting bigger and bigger, through the 70s, 80s, and 90s, every couple of years. So the idea is you run, instead of doing a single weather forecast, you run 50 forecasts every day. And the forecasts differ by, if you like, meteorological flaps of butterflies' wings. They just differ by tiny, tiny, tiny amounts, which are consistent with our uncertainty in those initial conditions. And the idea is, in a way, quite simple. When the atmosphere is in a very stable, predictable situation, then all those 50 members look like each other. They all resemble each other. The forecasts are pretty much identical. But as happens, when the atmosphere goes through a particularly unstable and unpredictable situation, then the forecasts diverge from each other, and you can get rapidly diverging solutions. And that, at least that warns the forecaster, that we can't make any very specific prediction today, and the best you can do is some kind of probabilistic prediction. So this is now pretty much used universally around the world, and it's kind of really, I would say, transformed the reliability of weather prediction into a science that is now, I would say, pretty reliable.
Yeah, and then in part two, what you do, which we will discuss later, is apply that same way of thinking to pandemics, economics, crashes, even wars. That's the essence of part two, to see the practicality of this in today's world.
That's right. That's exactly right.
Then in part three, understanding the chaotic universe and our place in it, you then leap off the bridge.
Well, I mean, it's great to be able to write a book where you can, if you like, let your imagination and your prejudices and your sort of feelings about things run wild in a way which, let's say, in a peer-reviewed journal, you might have more difficulty.
So it's great fun, and we'll get to it. One of the themes will be counterfactual worlds. which is a very deep idea in philosophy that you apply very broadly to some of the biggest questions that we have challenging current belief, as I said, in quantum mechanics, free will, and others.
If I could just add very briefly that the whole point about talking about counterfactual worlds is that the ideas about chaos and the geometry of chaos lead you to this new perspective on counterfactual worlds. It's not something you just dream up out of the blue. You're forced in this direction by the geometry of chaos.
Okay, so that's what we really want to focus on now. I want to go into part one in some depth, and that is one of the keys, because that certainly is a major discovery. In fact, you make what initially seemed to me as an astonishing claim, 6 standard deviations away from normal claims, that Ed Lorenz's discovery of fractal geometry of chaos is not only one of the greatest discoveries in chaos theory, but is one of the greatest in all of science, the concept of deterministic non-periodic flow. Go into that in some depth to explain what is the significance of that discovery?
I mean, the first thing to say is Lorenz discovered. I mean, Lorenz himself had a hunch that the reason why weather can be so difficult to predict is actually not because weather is a very complex system, but that there is something fundamental about the nonlinear structure of the equations which make it unpredictable, and that could be teased out with a very kind of set of equations which are really very simple to look at, but have kind of complicated consequences. And there, by the way, he was also 6 standard deviations away from conventional wisdom. I mean, you could ask 1,000 scientists and you'd say, why is a turbulent fluid so difficult to predict? Why is the weather so difficult to predict? Why is the economy so difficult to predict? And they would all say, because these are really, really complicated systems. There are billions of degrees of freedom. They're bound to be unpredictable because they're so complex. And completely against the odds, he showed, this was not necessary. This was not a necessary thing. So he came up with these 3 very simple equations, which had this property of not being able to be predicted indefinitely into the future. But more than that, what he showed was, the thing that bothered him was the 3 equations. So the 3 equations are equations in 3 variables. And so you can think of these 3 variables as defining a kind of 3-dimensional space. It's not exactly physical space. It's what we call state space, the state of the 3. So a state of the model is a point in this 3-dimensional space. And the question he asked himself was, what if I run my equations forever into the future and just watch how this point evolves? Does it just fill the whole space, or does it fill a subset of the space, or what happens? And he realized it filled a subset of the space, but then he couldn't figure out what this subset was. It looked like it was a solid, but then he realized it couldn't be a solid, and then it could be a complicated surface, but it couldn't be that. Anyway, it's eventually led him to this idea that it was a fractal. And, this has extraordinary consequences in a number of fields, but I think the most fundamental consequence is for some of the things that we'll talk about, which is really about reinterpreting fundamental physics, the role that this type of geometry could play in fundamental physics.
Yeah, so it's a huge conjecture to be charitable, and you deal with this. You introduce it in your first chapter. We also talk about the complexity of a 3-body problem, time and reversibility, and then how this theory can affect every science. It's not just weather and economics, which seem obvious, but it has deep implications for every science, and as you were saying, even to the most fundamental level. And then in the geometry of chaos, which is your second chapter, you begin to lay down the gauntlet by saying chaos, that this way of thinking can underlie quantum mechanics and the Schrodinger equation, which sounds like a Buddhist denying Buddha. Um, uh,
One of the practical aspects of this geometry is that it does explain this notion of intermittent instability, why systems can appear, even chaotic systems can actually appear quite predictable for long periods of time, but then suddenly undergo catastrophic unpredictability. And I actually start with an example from planetary motion. There was a really beautiful animation which I provide a link to, of four planetary bodies going around each other. And if you looked at the animation, you would think, oh, this is so boring. They're just going around each other in what look like ellipses and nothing much is happening. But then suddenly, completely out of the blue, these planets zip off to infinity. They cross some subtle instability, and they all diverge from each other. And this kind of feature is brought out really clearly when you look at the geometry of chaos, how these instabilities are localized in particular parts of the geometry.
and when you describe geometry, you mean how each individual case will create a one kind of reality, and as it changes, it fills up this space. And the naive assumption, I think what I would assume, is that eventually it would just cover the space evenly, but that's not the case, and that's the point of
That's right.
geometry. It's not just
That's
a
not the
it's not
case. And
it's not just the case of just smoothly filling it out, maybe not perfectly at all at once, but like you flip a coin 1,000 times, you'll get closer and closer to 50%. That's not what happens.
that's right. The geometry, the space does not get filled out like a solid, and there are always these gaps. And you can zoom in to regions which look like they're completely solid, but there'll be gaps, and the gaps are kind of super important. This is a type of geometry that was actually first discovered by George Cantor back in the 19th century, and his mathematical colleagues at the time thought he was crazy. They just didn't believe it, and it kind of sent him into a depression that he never actually recovered from. But Cantor's geometry underlies Lorenz's geometry, and in my view, underlies a lot of the world that we live in and observe.
So as I looked at from your book, I got four kind of characteristics of Lorentzian geometry of chaos, and tell me if this is correct, and then describe each one very briefly. I had state space, geometry of an attractor, time irreversibility, and then the Cantor set of fractal geometry.
Yeah, so let me just briefly go through those. I mean, state space is a little bit of an abstract idea, but the example I used in my book was thinking about buying a pair of trousers, because if you buy a pair of trousers, you have to decide what waist size to buy, what length of leg to buy, maybe what color the trousers should be, what material the trousers should be made of. So you could think of a four-dimensional space where the waist dimension was one direction, the length was another direction, the color was a third direction, and the type of material was a fourth dimension. And then a trouser would be a particular point in that four-dimensional space. And if you vary the point around, you're either varying the waist size or the length size or the color or the material. So that's a kind of concept of state space. And Lorenz's state space is actually even simpler. It's just three-dimensional, so you can visualize it. So three variables, three dimensions. And what happens is that if you let Lorenz's equations go on an initial point in this state space, and you just wait for a long time, you find out it traces this strange looking geometry in the state space. And what Lorenz realized, to understand what that geometry is, he went back to the work of Cantor, who discovered this notion of a fractal, and realized he was really looking at an example of Cantor's fractal geometry. The thing that's remarkable about this is that Isaac Newton would have understood Lorenz's equations. These are equations using Newton's calculus. So Newton would have said, oh yeah, those are three coupled differential equations. I understand that. But if you said to Newton, those equations generate a kind of fractal geometry in the state space of those equations, he would have been completely flummoxed by that idea. Because for him, geometry was, the geometry of Euclid. It was spheres and ellipses and things like that, which are very smooth. This is the complete antithesis of a smooth geometry. Now, the thing about this geometry is called an attractor, because no matter where you start in state space, the equations draw you down onto this attractor. They suck you onto the attractor, or suck the point onto the attractor. You never see the opposite happen. Once the point is on the attractor, it never jumps off again. So there is a kind of irreversibility in time, that states get attracted to the attractor, but they never leave it. So it's a completely new type of thinking.
The word attractor has sort of a teleological tinge to it, that it sort of indicates it's always been there in some sense, and when the opportunity comes, it's going to suck you in, as you just put it. I'm sure you don't mean it in a teleological sense, but
well, in a sense, I probably do mean it like that, because I do think, in a sense, the geometry of the attractor, it has a kind of timeless notion to it. As a geometry, it kind of exists outside of time. States evolve on the attractor, but the whole thing doesn't, you can't say it only exists at a certain time and not before that time or after that time. So it's kind of timeless. So I think when we come to talk about fundamental physics, that's probably an important
and
point.
especially when we talk about alternative concepts of God, which are the very last few pages of the book, we'll get back to this attractor and the multidimensional faces it has. Okay.
Right.
The next chapter, you again digging more deeply into this fundamental concept, which is the way that chapters in part one work, and it really helps us to understand. So I think the organization of part one was excellent for a very difficult subject to understand, because it's actually simple to understand. It's just so radically different from the way we think normally in physics. So the third chapter you call Noisy $1,000,000 Butterflies, and that's the classic Lorenz's, as you point out, 1969 AAAS speech. Does the flap of a butterfly's wing in Brazil lead to a tornado in Texas? I think we're all familiar with that, but what you do is you show the deep mathematical significance. Now, what I want to read is a complicated quote that you have in the book, because to me, this was shocking and an eye-opener. And indeed, you after you gave the quote and explained the Lorentzian thing, you called it the killer concept. I did a search in your book. You used the word killer once, and this is it. This is the killer. Okay, I'm going to read it. I'm going to read it slowly because it's a little complicated. So certain formally deterministic fluid systems, which possess many scales of motion, we can understand that, are observationally indistinguishable from indeterministic systems. Specifically that two states of the system, differing initial conditions, by a small observational error, very, very small, will evolve over time into two states differing as greatly as randomly chosen states of the system. Now, here's the point. Within a finite time interval, which cannot be lengthened by reducing the amplitude of the initial error. Now, what that means is that there's some crazy fun, because I would have naturally thought you could reduce the time interval by reducing the amplitude, so that. But you're saying, and Lorenz is saying that you can't do that. I mean, that is unbelievably counterintuitive, and that's the one place you use the word killer.
Right. And I have to say, this is something that people, even in the field, do not understand well. If I take what I would call a conventional chaos model, the sort of one that Lorenz actually formulated in 1963, the one that sort of made him super famous, then as you correctly say, you could say to me, I want to make a prediction with that model for a certain amount of time in the future. And it kind of doesn't matter how far ahead that time is. You could say a day, a month, a year, a decade, a century, a millennium. Whatever time you give me, I can tell you how accurately you need to know the initial conditions to make that prediction. So this is what mathematicians would call that the system has continuous dependence on initial conditions, which means that, as the error in the initial conditions gets smaller and smaller, so you can predict out further and further.
That just seems incredibly intuitive. I mean, it
Yeah,
seems
that's
like...
right. That's completely intuitive. Lorenz, in 1969, which led to his famous butterfly talk at the AAAS meeting, American Advancement of Science meeting, asked this question not about his simple 3-component model, but about the full infinite dimensional, what it's called infinite dimensional equations of fluid mechanics, where you have, big eddies, small eddies on smaller eddies, and so on. The atmosphere is a good example. It's got cyclones. There are clouds embedded in the cyclones. Within the clouds, there is turbulence, and within the turbulent eddy in the cloud, there's smaller scale turbulence. So he asked the question, if the uncertainty was confined to one of these very small scale parts of the system, how long would it take for that uncertainty to propagate up to larger scales and eventually affect the accuracy of your largest scale, if you like, the cyclone scale? And what he found was that the uncertainty, as you go to smaller and smaller scales, the uncertainty grows faster and faster. So, for example, in a weather system, it may take a couple of days for an error in a big low pressure system to grow. But if you have an error if you're trying to simulate a cloud, it may only take a couple of hours for a small error in that cloud to grow. And if it was a piece of turbulence within the cloud, that's even smaller scale error would grow maybe in time scale of minutes. And he put this all together in a mathematical model, which suggested, as you say, that there may be an absolute horizon, a limit to predictability, which, even when the initial error is infinitesimally small, cannot be exceeded. This is an example of what is sometimes called a singular limit. And maybe I can say it this way, that in a hypothetical deterministic, you see, the equations of fluid mechanics are deterministic. So you could say, if you precisely, absolutely 100% precisely knew the initial conditions, then you could make a prediction into the future, arbitrarily into the future. But what this singular limit says, that even if your uncertainty is infinitesimally small, it will destroy the ability to predict beyond a finite time. Now, I have to say, this actually has not been proven rigorously, and it's one of the open problems in the so-called Millennium Prize problems of the Clay Mathematics Institute, proving that this is actually rigorously true, that effectively that Lorenz's conjecture about the equations of fluid dynamics having finite time predictability is literally true. We don't actually know rigorously whether this is the case or not. So at the moment, it's a bit like Fermat's last theorem. It's Lorenz's last conjecture, if you like, which hasn't been proven. And if anyone can prove it one way or the other, then there's $1 million at stake.
It to me is, in all my science career, going back 50, 60 years, it's one of the most counterintuitive thoughts and results that I've ever seen.
Counterintuitive, but nevertheless rather beautiful, and it comes about, as I say, through the fact that uncertainty, the growth of uncertainty is scale dependent. So as you go to smaller and smaller scales, the growth rate of uncertainty increases, and the whole thing, as you get to tiny scales, the uncertainty is growing so quickly that it's just killing your predictability off.
So one practical application of this, which you bring up, which I want to verify, is even with perfect observations of the weather, you cannot predict ahead for more than about 14 days. So the idea of predicting ahead, say, 3 weeks would be, correct me if I'm wrong, it would be in principle impossible even for an omniscient being like Laplace's demon that knows everything and can calculate forwards and backwards. And you say that's the real meaning behind the butterfly effect. Is that right?
Well, I have to be a little bit careful here because my colleagues will complain at me bitterly if I don't get this quite right. I think what is that statement is true if one is predicting the the exact pattern of weather. So whether a particular cyclone will hit on the 14th day or the 15th day, that sort of prediction, we're getting to the limit of predictability by about 2 weeks or so into the future, which is very unlikely, I think, that we'll exceed. But having said that, I should just point out that there are reasons for being able to make longer range predictions of a more generic sort. And the classic example, which I guess people in the US are familiar with, is the El Nino event in the Pacific Ocean, which is this irregular warming or cooling of the Pacific, which we can probably predict pretty well, which can predict pretty well 6 months, even perhaps a year ahead of time. And when there's an El Nino event, it affects the statistics of weather. So you're still not predicting, still can't predict a particular cyclone more than a couple of weeks or so ahead. But you can say over this coming season, the cyclonic activity will be stronger than normal or weaker than normal, and therefore it'll be rainier than normal or drier than normal, in a statistical sense. So I'm just trying to distinguish what Lorenz's paradigm is telling us is about the detailed prediction of weather. One day after the other is probably limited to around 2 weeks or so. But there are certainly possibilities to predict the kind of statistical fluctuations of weather on a longer time scale because of the coupling to the oceans. And of course, the whole climate change thing is predicated on that we're doing something to the atmosphere which is changing the statistics of weather in a longer term sense.
So you end part one by introducing quantum uncertainty, and then you deal with that very extensively in part three. But clearly, this is a deep motivation of the book because it pops up every so often, and it is extraordinarily radical. So the critical question, I think, is quantum uncertainty, which everybody recognizes, epistemic or ontological, as you've said? Epistemic means it's just a question of our capacity to know, or ontological, is it a fundamental property of the system that is immune to any maximum knowledge that we could have? And you posit that the way of thinking of ensembles could be the way to distinguish between these two, and it's so that the thinking would be that quantum uncertainty would be epistemic, which is a radical change, and that justifies that famous subtitle where you're linking quantum mechanics and climate change, and the linkage is through this ensemble thinking of the geometry of chaos.
That's right. And by the way, I'm not the first to suggest about an ensemble interpretation of quantum mechanics. And famously, Einstein himself said that he thought the wave function in quantum mechanics was just a representation of an ensemble of worlds, and one of the worlds turns out to be reality, but we don't know which one of the ensembles. It's like a weather forecast. One of the 50 weather forecasts, when we run an ensemble of weather forecasts, will turn out to be pretty much what happens in the real world. But at the time we make the ensemble, we don't know. So that's what Einstein believed. It was similar to that. But of course, that's not the way in which 99.9% of physicists think about it. And that comes because of a very famous result called Bell's theorem, And interestingly, this week, the 2022 Nobel Prize was given to three eminent experimental physicists who showed that this, if we're going to talk about Bell's theorem, that a certain experimental result, which traditionally seems to rule out Einstein's ideas.
Let's get into that. Let's
Validity.
get into that into part three, because that we're going to focus on that in part three. Okay, so that gives
Right.
the overview. Part one was some heavy going to get through this because it's so counterintuitive, but as I've said, I really loved it and learned a lot. So now in part two, you apply these ideas to various categories that you've studied with climate change, pandemics. What I'd like you to just do is just give a very, very brief overview of some of these. You begin with in chapter 5, which is the first chapter in part 2, with two roads to Monte Carlo, which is a way of simulating probabilities. And you have this marvelous story that, well, first of all, you say that if the probability of rain between 6 o'clock and 7 o'clock at night over my city on a Tuesday is 80%. You go through a lot of things what that does not mean. So go through that because it gives a little bit of a flavor, and it's of the nature of probabilistic language.
Well, yeah, I mean, unfortunately, this is something, which does confuse a lot of people, because these days, every time you look at your weather app, there is a probability of precipitation, as it were, a probability of rainfall, and nobody really quite knows what it means. Does it mean, it's going to rain in 80% of my town or 80% of the time and all that sort of stuff? And that's not really what it means. If you have an ensemble forecast, there will be, let's say, you look at an ensemble forecast every day for a year, and then just select all of those occasions where the probability of rain was 80%. So that means that in the ensemble, you've selected these ensembles where in 80% of the ensembles it's raining, and in 20%, the remaining 20% of the ensemble, it's not raining. What you expect to find is that in reality, in those situations, so for that subset of ensemble forecasts where the prediction was for 80% rain, that in reality, it will have rained over your town in the allocated period of time, 80% of those occasions. I'm not sure I said that as well as I could have said it, but anyway, if you go to the book, you'll see the precise definition of what it means. So it doesn't mean it'll only rain in 80% of your town or 80% of the time. It's a statement actually comparing the probability with the actual frequency of occurrence of rain in that set of occasions.
Now you give this very practical significance in one of the great stories of the book that I love, where a friend of yours would ask, I'm having this dinner party and I don't know whether to put up a tent or not put up a tent, because if it's going to rain, I need to put up a tent. And it sort of says 50% or whatever. And the way you begin to address that question, because you're the expert on this and it's your friend, he was having a dinner party, he wants to know whether to put up a tent. You ask him, is the Queen coming to the dinner party?
Right.
And so explain why that's important.
Well, you see, at the end of the day, I think the message I want to put out here is that at the end of the day, knowing these probabilities will actually help you make a better decision. So my friend called me up and said, we're going to put a tent up. It was a wedding anniversary or something. Or at least they had the option to put the tent up. That was the thing. So should they do it? It was for about a week ahead, and they had that option. Obviously, it costs money to put the tent up. So if it was going to be bright and sunny, they wouldn't do it. So the question I asked, as you say, who's coming to the party? Because if the Queen was coming, and I told you there was a 5% chance of rain, you might still. It would be disastrous if you were the local dignitary and you caused the Queen to get wet. That would be awful. So, so in that situation, you might decide to put the tent up just with a small probability. Well, okay, the Queen wasn't coming. So how about the town mayor? I asked. So he said, well, why is that? Well, okay, if the town mayor got wet, I mean, it wouldn't be as bad as the Queen getting wet, but it's still slightly embarrassing. So you'd put your threshold up to maybe 20% chance of rain, let's say. Um, so
How about
I asked,
mother-in-law?
well, that was it. So I said, "Who's the most important person?" I mean, I think he got the drift then. So I said, "Who's the most important person?" And it was probably the mother-in-law. So then I had to ask him, "Well, what's your probability threshold, for the mother-in-law to get wet?" Because and then he said, "Well, I can't remember what the number is. Probably 40%."
I think 50%.
There was 50%. Okay, so then I went to look at the actual probability forecast. But the point is, and I think it was less than 50%, if I remember the story correctly. So, he'd made a decision. Now, the serious point about this, though, Robert, is that this is precisely how humanitarian organizations are making decisions about whether to send food, medicine, shelter, water, etc., to places that are potentially at risk from extreme weather before the event hits. So in the old days, they would just wait till the event happened, because weather forecasts, the old deterministic forecasts, were never that reliable and you couldn't be sure. But now what they do is they do that kind of mother-in-law, queen, town mayor calculation to say, how large a probability does the extreme weather event have to be for us to be able to justify, in terms of our financial, our finances and so on, to justify sending food, medicine, and so on in ahead of time. So they have a probability threshold that they've pre-calculated. And then when the event does occur with a probability that exceeds that threshold, they know they have an objective reason to go in and help people ahead of time. So this has really changed the way in which, disaster relief and humanitarian aid is being done. It's called anticipatory action, and it's really a big new area in disaster relief.
Enormously significant. Tim, let's go through some of the chapters in part 2 very quickly so we understand how the primacy of doubt thinking, the butterfly effect, and ensemble prediction can affect each of these really big categories. Climate change.
Right. I mean, I wanted to be upfront and honest about the uncertainties that there are in climate change. And I focus very much on what are called climate feedbacks, things like how do clouds respond to our emissions of carbon dioxide, because this will completely determine how much warming we get, but say by the end of the century. And we use ensembles because we don't have a precise description of clouds. We don't actually understand clouds in all their detail, and the models have different representations of clouds. So at the end of the day, we end up with probability distributions of things like global warming, which can range from 1 degree for a doubling of carbon dioxide up to, or just 1.5 degrees, let's say, up to maybe 6 or 7 degrees.
Wow, that's huge.
And of course, it's like the guy my friend who has to make the decision with the tent. It's up to us to decide, based on those probabilities, whether we want to take action to try to minimize the risk of climate change.
Good, and you articulated well the difference between the maximalist and minimalist positions, and the science that actually undermines both of those views in order to give a rational approach. Pandemics.
Well, I wrote the book during the COVID pandemic, and I was struck, actually, as the science of COVID prediction developed, how close the analogy and indeed the science of COVID prediction was with climate and weather prediction. And about halfway through the COVID pandemic, people started to write papers on ensemble prediction of COVID deaths and COVID hospitalizations. And these ensembles were based on multiple models that were developed in different institutes, precisely actually as the IPCC, the Intergovernmental Panel on Climate Change, do for climate change. They get groups around the world to run their predictions with different scenarios for carbon dioxide. And in a similar way, the COVID people then were doing similar types of work with predicting hospitalizations and deaths for different different policy scenarios. In other words, we let everyone interact and don't care about it, or we try to really restrict interaction. So I was kind of struck by that. So I wrote a whole chapter on the developing science of ensemble COVID prediction. And my only kind of thing at the end is to say that just as the World Meteorological Organization organizes these ensembles of climate change for the world, so I think the World Health Organization could do a similar job in coordinating groups around the world in producing ensemble pandemic predictions. And I'm sure this will happen, but I think it's still a bit more coordination needed before it does
The
happen.
analogy is very strong. It's not just a metaphor. It really, really works. Next chapter, financial crashes.
Well, you see, there was an interesting quote from a former chief economist at the Bank of England when the Queen came to visit the City of London a few years after the famous 2008 financial crash. And the Queen said, rather, why didn't you, speaking to the economist, why didn't you see this coming, this financial crash? And they were kind of rather sort of humiliated, I think, by this remark. And the chief economist said that it was there. So he used the word Michael Fish. So I have to explain for people outside the UK. Michael Fish was the forecaster who famously didn't forecast the biggest storm in 300 years in 1987, just a few hours, 12 hours or so before it happened. So the chief economist said this was their Michael Fish moment. And, it kind of struck me, and it seemed to. So then I actually started contacting a lot of economists and saying, are you guys applying the same ensemble techniques that we do in weather prediction? And I got a very discouraging response from most of them, saying that the science is not developed well enough and so on. But eventually I managed to track down a few people that were doing really interesting work with what are called agent-based models, where this ensemble technique can be applied. And I showed at the end of the chapter there were some encouraging signs that that we could use some of these techniques in economic predictions. The question is the 2008 financial crash an example of one of these intermittent instabilities? And it seems from this ensemble work that there's some truth in that, in fact.
When I read that chapter, I wondered this question, that what's the relationship between ensemble prediction, specifically in economics as you had it, with what's called systems dynamics, which was developed by Jay Forrester at MIT? Because when I was at MIT, I actually took that course with him and with Ed Roberts. And there seemed to be some kinds of similarities in terms of thinking, although that was much more deterministic and it had, 1,000 variables to build an economic model.
Well, I think there possibly are. I mean, as I say, the current sort of buzzwords are agent-based models, and I think maybe there's some connection there. But I think the key idea, though, is can we develop this to the extent where we can identify, what are the key uncertain variables and uncertain parameters and uncertain representations, if you like, of agent-agent interaction, and develop, credible ensemble systems where essentially you can use the spread of the ensemble, the how much the members deviate from each other, as a kind of measure of how predictable the situation is. I think, to be honest, we're still the jury's still out on this, but there's some encouraging signs that.
Yeah, it seems fearsomely complex to do, but the results that you've had in weather and also in pandemics gives one a reason to pursue it.
I mean, one thing that came out very clearly in my attempts to find out what's going on in economics is that a lot of people still seem to cling on to this idea that should be some very simple kind of mathematical principle that will somehow, can be used to predict the economy. And my experience in weather prediction is that is just not, that's not the case. That to a certain extent, a brute force, solution of the equations of fluid dynamics, is the best way to make a weather forecast. And it uses, it doesn't use elegant mathematics, it uses kind of engineering mathematics. And my plea to the economists is to kind of embrace engineering mathematics to their heart, because I think that's where the biggest gains are going to be made. Don't pretend that there's some elegant mathematical theorem that's out there that's going to predict what's going to happen to the banks and things in the next 6 months.
Let's go on to part 3, our most fun part, and what most directly relates to closer to truth, because you deal with foundations of quantum mechanics, free will, consciousness, the different ways of understanding the nature of God. So those are all our core topics. So let's start with quantum mechanics. And you say, my own belief is that methodological reductionism, that smaller is always more fundamental, as you get down in the physics, to particle physics and then subatomic physics, maybe string theory, is a flawed philosophy. That fundamental physics is going 180 degrees in the wrong direction because of that. That is, if I use the word heresy for that, that would not be an overstatement.
Right. Well, I say that for 2 reasons. First of all, I mean, which every physicist will kind of agree with me about, is that we have these incredibly long-standing problems which haven't really moved forward a great deal. And the one that I worked on in my PhD work back in the 1970s was this problem of quantum gravity. How do we synthesize quantum physics and gravitational physics? And, people claim for a long time that string theory would do it, but it's not. People have been at that for a long time, and it seems to have ground to a bit of an impasse. And then, of course, more recently, with the issues of dark energy and dark matter, these have thrown up problems that current physics just doesn't seem to be able to address terribly well. Now, on top of that, the whole philosophy here in my book is that this geometry of chaos, the geometry that underpins these chaotic systems, is itself a fundamental property of nature. And the geometry encompasses the holistic side of the chaotic system. If you describe the geometry, you're describing the entirety of this chaotic system. So if the idea is then in part 3 is to say, well, could the whole universe be thought of as a chaotic system? If it can, does it also have a chaotic, what's called a strange attractor, a fractal attractor in cosmological state space? This, the trouser state space, but for very large, large trousers, if you like. And are the laws of physics? So this is the key point. Could the laws of physics, at their most fundamental, be describing the geometry of this fractal, cosmological fractal? And could that provide us new insights? So that's what we can talk about into quantum mechanics. I do believe it can. If that's right, it's saying that this geometry is the fundamental quantity, and that's a property of the whole universe. It's everything that's in the universe altogether. So it's not something that you're going to probe by just going to smaller and smaller scales or bigger and bigger energies in a particle accelerator. It's a property of the largest scales in the universe as a whole. So it's a complete antithesis of methodological reduction.
Yeah, it's really an astonishing conjecture. It's we talk about top-down thinking if we want to explain consciousness, but this is the most massive top-down thinking that you can imagine. Because obviously the holy grail of physics is quantum gravity, unifying general relativity and quantum mechanics. And as you said, it remains elusive. Most physicists think that if there is a problem, and there may be, you have to ask what's wrong with general relativity. And you're asking, maybe we should say, what's wrong with quantum mechanics?
Absolutely. General relativity is it's a remarkably beautiful theory. It's a non-linear theory. I have a great, non-linearity underpins absolutely everything in my book. Chaos theory would not exist if systems were linear. A linear system is one where the outputs are proportional to the inputs, or are proportional to inputs. So yeah, general relativity is beautiful, and we understand general relativity pretty well. I mean, there are still some issues perhaps with black holes and singularities, but broadly speaking, we understand general relativity. By contrast, we just don't understand quantum mechanics. We can apply the rules of quantum mechanics. I often think, we're like computers. As kind of, a computer doesn't understand the weather equations when it makes a weather forecast. Similarly, we don't really understand quantum mechanics. We can apply the rules and they give perfectly normal sort of answers and things, but we just don't understand what's going on. And I think that is a problem, and it really is the problem that makes it so difficult to combine gravity and quantum physics together.
So, Tim, you go on from there, not satisfied with one heresy, but now you go on to call the accelerating expansion of the universe potentially an illusion. And you say that some regions of the universe where entropy may be decreasing. So 2 more heresies. And then dark matter may not be a new particle, but rather the effect of space-time curvature on the invariant set. So you've collected an ensemble of heresies.
Yeah. Okay. I mean, these are, So my basic hypothesis is that, as we were saying earlier, the universe can be thought of as a chaotic system evolving on this fractal geometry. I call it the invariant set. That's the sort of technical mathematical phrase that would be used. One way of disproving that idea would actually be if the universe really does end up in a heat death. So it just expands, it accelerates away, and then eventually just dies and nothing happens. It continues expanding and accelerating forever, which are some of the cosmological models. So that would be inconsistent with my idea. But my saying that dark energy may not, we don't really know what it is. It could potentially not. It could just be a local manifestation in our part of the universe of acceleration. And also, we don't know whether it'll continue forever. I mean, there are certainly theories where it reverses. So I don't see that as a major heresy. But the really important part of all this is what the implications are for quantum mechanics.
You then go on to apply the thinking of ensemble forecasting and the importance of noise in ensemble thinking to our brains and see that perhaps creativity, the ability to think of new things, is not disrupted by noise, but rather enabled by noise.
Yeah, I mean, there's very little doubt that we have so many neurons in our brains, 80 billion, and they're powered by such a tiny amount of energy, 20 watts, 20 joules per second, which is 6 orders of magnitude less than a typical supercomputer takes. The brain actually is noisy, and noise often is most apparent when we're multitasking. We're walking down the road, we're listening to the birds cheep, can see various things. We're doing lots of things. And quite often, that's when we have our flashes of insight. That's when, if you talk to all the Nobel Prize winners, they'll often tell you, I had the critical idea when I was crossing the road, as Roger Penrose would say, or Henri Poincaré catching a bus somewhere, or just doing something very, not focusing, not concentrating hard on the problem. And I think it's this kind of when we're relaxing or when we're multitasking, that's when we're most susceptible to noise. And I think what noise does then is give us these sort of creative ideas that maybe in the light of day, 99% of them we'll realize are rubbish ideas, but every now and again, 1% gets through. And that's the eureka moment that changes things. So I think, without that uncertainty and noise in the brain, we would not be the creative species we are. So, noise is not, we've evolved to make constructive use of noise. And I think I think that actually has important messages for development of AI systems. Doing it in a deterministic framework just won't get anywhere.
Your last chapter deals with the big questions of free will, consciousness, and even God. And you use the primacy of doubt and the geometry of chaos to contribute to these debates. You don't claim you're answering all the questions, but you are saying, I was very skeptical when I came to these chapters because we've been dealing with this for 20 years. But you do add a new way of thinking to each of these. Be it right or wrong is maybe not so important, but you kind of alter our way of thinking. So I'd like you to describe very briefly for each of these, start with free will, how the geometry of chaos can give a new perspective.
Yeah, I mean, the problem with free will is that it's a problem if you believe in determinism, because then you say, well, everything I do today was determined by whatever the universe was like yesterday. And what happened yesterday was determined by what the universe was like the day before. So then, everything kind of goes back to the Big Bang initial conditions. Everything was determined by the Big Bang. And then you have this problem of moral responsibility. Do you let Hitler off the hook because his actions were determined by the initial conditions at the Big Bang? So he had no choice than to do otherwise. He had no choice in doing what he did. The problem is that the opposite of that, indeterminism, doesn't really help, because then it just seems like what people do is random, so they don't have any responsibility either, moral responsibility either, because what they did was somehow just random noise causing them to do what they did. I mean, this has kind of bothered me for quite a while. And it seems to me that this notion of the geometry of chaos does actually provide at least it provides another way of thinking about this problem, and it may help us out of this dilemma. The idea really is that it's this geometry that's the fundamental thing. It's not the Big Bang initial conditions are not fundamental in this picture. It's the geometry of chaos. And in a sense, today, what happens today is as important and as fundamental as what happened, 13.8 billion years ago. It's this geometry that's important. I'm reminded there's a famous phrase by the physicist John Wheeler, who talked about general relativity, and he said one way of thinking about general relativity is that space tells matter how to move, and matter tells space how to curve. So there's a kind of duality between matter and space. And I think of our actions as human beings and the geometry of this chaotic attractor, that my postulate is that the universe is a chaotic system with a fractal geometry. There's a kind of duality here with Wheeler's aphorism, in the sense that the fractal geometry is telling us how to behave, but similarly, how we behave is determining the geometry of the fractal attractor. So it seems to me that there is a case here for keeping determinism, because after all, these fractals are deterministic, but at the same time allowing for this notion of moral responsibility, because what we do, in a sense, informs the geometry of the attractor as much as the geometry of the attractor informs us. There's a kind of a self-referential notion here between this geometry and our behavior. Now, look, I'm not saying I have a complete theory of this, but it seems to me it gives a new perspective, if you like, on this really old problem.
I agree. It does give a new perspective. There are obviously a lot of questions, because if this invariant set and the geometry of the whole universe existed prior, what we do today can't affect what happened before, backward causation or retro causation. There's a lot of issues, but it gives a new perspective. Let's go on to consciousness.
Consciousness is tied with I see another aspect of free will, which people don't seem to ask very much, is why do we have such a visceral feeling that we have free will? I mean, we all feel it. Even kind of dyed-in-the-wool determinists kind of feel,
Sure.
there's some very visceral feelings. There's something in the brain. Now, this notion of the laws of physics being determined by the geometry of this fractal means that there are neighboring worlds on this fractal geometry, which, by virtue of the fact that the equations are the geometry, these neighboring worlds are somehow also contributing to the evolution of our own world. Now, if there are quantum mechanical processes in the brain which are playing a role in our cognition, as, for example, Penrose and Hameroff would claim, and perhaps others, then maybe our perception is the way in which quantum mechanics affects our cognition and perception of the world is to give us a kind of a weak conception of these neighboring worlds on this fractal geometry. And these neighboring worlds are examples of counterfactual worlds. They're worlds where we might have done something, but we didn't. And my claim is that our visceral sense of free will actually arises because we have some conception about these neighboring counterfactual worlds. Now, it seems to me that that argument may also then generalize to talk about the notion of consciousness as well, because, I used the example when I was writing my book that every now and again I would look up from my book and see my cactus, which I still have on my windowsill behind this computer screen. I became conscious of the cactus. But when I was writing the book, I mean, the photons were scattering off the cactus and going in my eye, but I wasn't conscious of the cactus because I was focusing on something else. So the question arises, what do we mean by being conscious of the cactus? And it means that somehow we perceive the cactus to have a distinct individual realism within the world of objects in my study. And that notion of it being an independent object means that it could potentially, in this counterfactual way, it could have been in a different place to where it actually was. And again, this notion that maybe our brains can have some weak cognition of these counterfactual worlds on the invariant set is what gives us this notion that objects have an independent existence. And that's really, seems to me, what underpins our notion of consciousness, because it's being conscious
Again,
of independent.
it's a new perspective. I appreciate it. I think there's a distinction between attention to the reflection you're seeing, and the phenomenology of inner awareness are more complex issues. But if you carry through the concept of the cosmological invariant set and the counterfactual worlds, you make the additional claim that there could be a kind of afterlife where we and our loved ones are coming back in some future epochs of the universe on trajectories in state space close to the present one, but none precisely the same as the present one.
Robert, you're making a really good point, which is that on these fractal attractors, what we're actually looking at is the evolution of a state as it goes around state space, and it eventually comes back to a place which is close to, but not quite the same as where it started. And these, what I call these counterfactual worlds, are actually worlds in some future or past epoch of the universe. The universe, they're not really parallel universes, they're just future manifestations of our universe. The fact that the universe gets back to a point which is close to the present means that, we will, if this is right, we will get back to a world where we have our loved ones, we're in the world that seems familiar, but things will be slightly different and we'll make slightly different decisions. Some will be better, some will be worse. And I find that a kind of a comforting thought if it's true. the idea of going to a perfect nirvana where everything is perfect just somehow doesn't seem quite right to me. But going back to a world where we have chances to do things over again, I find that somehow, and where we'll meet our loved ones and so on again. And as I say, we'll make a hash of some things, but maybe other things will do better. I find that a kind of comforting philosophy.
Well, it articulates well with some Eastern philosophies in terms of cycles and things, as opposed to the Abrahamic religions of linearity.
But they're never precise cycles. This is the key point about chaos. Things are never precisely cyclic. They come back close to being cyclic, but then diverge again.
So the implications, you would say, again, the last thing in the book is about God, is that this cosmological invariant set of the geometry of chaos for the whole universe could be considered a logical alternative to the traditional God, in that it's timeless. It is certainly creating what we consider the real world, and it's sort of a multi-dimensional object that has many guises that perhaps could represent the multifaceted face of God.
It's a possibility. I'm not going to I'm not going to try to preach on this in any way, but it's a kind of
You're not starting a new religion, right?
I'm not starting a new religion, but it kind of ticks a lot of the boxes, and it has some appeal to me. I mean, I don't sort of dwell on this in my day-to-day life, but it's an intriguing idea, and maybe it just needs thinking through a bit more. But it seems to tick a lot of the boxes for somebody with a scientific mind that doesn't want, it doesn't want somehow things which transcend physics, because I don't think there's anything I'm proposing. It might transcend a lot of orthodoxy, but there's nothing that's non-physical. I don't violate any principles of physics, so far as I'm aware. So this seems to me a plausible way of thinking about God for somebody who is a scientist at heart.
Look, I have one final question, and that is, what is the articulation between these multitude of trajectories on the invariant set? How does that relate to the so-called multi-world interpretation of quantum mechanics? I mean, they're very different in their mechanisms, but the results are kind of the same.
You're right in a sense that that they both postulate these many worlds. I would say, just from what we were talking about, in my case, these are actually not many worlds. It's our own world that has evolved through multiple epochs and come back close to where it is now. So it's actually just one world going through a kind of a very, evolving on this fractal geometry. So from that point, it's different. But on the other hand, you're right. But I think where the sort of standard many worlds Everett interpretation of quantum mechanics is an attempt. So let me tell you what I think. I'm going to get many people who are many worlds people complaining about this, but many worlds theory or interpretation is an attempt to interpret the Schrödinger equation literally. And I think there are many, many, many problems with many worlds. For example, they talk about branching universes sort of splitting. Now, I've never seen any rigorous mathematics describing how a universe splits or branches. And I think many worlds theory has problems in tackling that. So my approach is not to try to interpret the Schrödinger equation, but to say there is actually something deeper than the Schrödinger equation, for which the Schrödinger equation is a kind of an approximation. And I could tell you in more detail what I mean by that, but I think we've run out of time, so I won't. But so at a sort of technical level, this is really quite different to many worlds. But in the point of view of it has a flavor of many worlds. I agree, there are some qualitative similarities. Qualitative, but not quantitative.
Tim, I think you have given us a remarkably fresh and novel approach to understanding all things that are happening, not just on the practical level of climate change and economics and pandemics, but in terms of a fundamental way to think about the existence of all reality. And I really applaud you for that. I think that's terrific. As I said at the opening, it's brave because I'm sure there'll be a lot of critique, but I think it's a very important contribution to thinking and kind of disturbing the status quo, which is and basing it on hard science and things we know to be true. Where you take it, people can argue with. I'd argue with some of what you said with free will and consciousness and God, but you know, we've been going 22 years on Closer to Truth, still haven't come to the truth. People always say closer to the truth, and I always say it's not the truth. It's just present progressive, closer to truth. So
Right.
I think you have made a major contribution to closer to truth, not closer to the truth.
Thank you, Robert. The thing I would say is that I can do this in my stage of my career because it kind of doesn't matter to me a great deal or whether I get a lot of criticisms or not. I do worry, though, that a younger version of myself, making such statements might well hinder my career, and that kind of bothers me a bit. That can be the case.
No, I'm sure that's the case. But I'm very happy that you're able to do it now. As I said, I love the book. I recommend it to everybody. The Primacy of Doubt. Viewers can also watch hundreds of videos on foundations of quantum mechanics, consciousness, free will, and alternative concepts of God, for those who want that, on the Closer to Truth website and Closer to Truth YouTube channel. Tim, it was a great pleasure meeting and reading your book. I look forward to more conversations in the future. And to everyone else, thanks for watching.
Thank you.
Thank you for watching. If you like this video, please like and comment below. You can support Closer to Truth by subscribing.